based on the relative motion, we can calculate what's called a relative kinetic energy. It turns out, essentially what we're doing here is this. We have, remember, x1, y1, and z1. What are those? Coordinates of particle 1, right? And you have x2, y2, and z2 are the coordinates of particle 2. Essentially, what we've done is we are transforming our coordinates into big X, big Y, big Z. What are those big letters? Center of mass coordinates. And little x, little y, little z. So this is really nothing more from a mathematical perspective, nothing more than a transformation of coordinates. Okay, just a different way of looking at it. Just like when you did x, y, z. Okay, you could have used spherical polar coordinates r, theta, and phi. Okay, so it's just a different way of looking at the same thing. So your relative kinetic energy can be shown to be 1/2 mu v squared, where v is the relative speed and mu is the reduced mass. Okay, derivation for this is in your textbook. Okay, let me go straight to the end here. Further information, section 10.1 in Atkins. Okay, page 357. All right. So kinetic energy due to the relative motion is equal to 1/2 times mu times v squared. Notice it's very similar to the formula for kinetic energy. What's the formula for kinetic energy? 1/2 mv squared, right? So it's like an effective kinetic energy, but instead of using mass, you use what's called a reduced mass. So this mu right here, Greek letter mu, is a reduced mass. The definition of reduced mass is this. It's m1, m2 over m1 plus m2. Question, why is it called reduced mass? Well, let's see. How does mu compare to m1? Okay, mu, let's rewrite that. Mu equals m1, m2 over m1 plus m2. Right, that's your formula. Okay. What's the ratio of m2 to m1 plus m2? What's this number going to be? What's the mass of particle 1 divided by the total mass? What number would that be? Less than 1? Greater than 1? It's going to be less than 1, right? So in other words, you're saying that your reduced mass is less than m1. Well, let's look at it from the perspective of particle number 2. Oh. Let's compare. Instead, what's m1 divided by m1 plus m2? Again, less than 1. So you can also say that mu is less than m2. That's why it's called a reduced mass. Okay. So one way to think about it is that basically it's an effective mass, okay, that you use to calculate the relative kinetic energy. So let's look at the example given here. Let's say you have a 1 kilogram mass moving 1 meter per second to the right, and another is moving 1 meter per second to the left. Let's calculate the relative kinetic energy. What did we say the relative velocity was? We figured this out earlier, was negative 2.0 meters per second, assuming the particle that's moving to the right is particle 1, and the one that's moving to the left is particle 2, right? So negative 2.0 meters per second. So what's our reduced mass here? They're both 1 kilogram mass, so 1 kilogram, m1, m2, divided by m1 plus m2. So 1 times 1 divided by 1 plus 1, 1/2 kilogram. Okay? Let's see. So what is our relative kinetic energy? Or the internal kinetic energy? 1/2 mu v squared. And that is how much? 1/2. Our reduced mass is 1/2 kilograms. Our relative speed is 92.0 meters per second, and the whole thing is squared. So that's 1/4 times 4 meters squared per second squared times kilogram. So what's a kilogram meter squared per second squared? That's a joule. So your relative kinetic energy is 4/4. This is 1, so it's 1 joule, right? 1 joule. What is our translational kinetic energy? Let's see, what happened to our center of mass? Particle number 1, 1 and 2, they're both 1 kilogram, right? This one moved 1 meter per second, and this to the right, and this is 1 meter per second to the left. What do you think? Where's their center of mass to begin with? Right in the middle, right? Did the center of mass move? Okay, in this particular case, I may try to make this as simple as possible. The center of mass has not moved because they both moved an equal distance from the center, right? So what's our translational kinetic energy? The movement of the two particles as a whole, as tracked through their center of mass, is 0. So translational kinetic energy is 0. So what's our total energy? K translational plus K internal or relative would be 0 plus 1 joule, which is going to be 1 joule. Okay, that's our total kinetic energy. What about if we did it the other way? Are we going to get the same thing? What is K1? 1/2 M1 V1 squared, and K2 is 1/2 M2 V2 squared. So what is that? 1/2. M1 is 1 kilogram. V1 is positive 1.0 meters per second. I square that. So this is equal to 1. 1/2 times 1 times 1 squared. 1/2 joule, right? So kinetic energy of particle 1 is 1/2 joule. What's the kinetic energy of particle number 2? Also 1/2 joule. What's the sum of the two? 1 joule. Same sum. Two different ways of looking at the total energy of your two particles. You can say particle 1 and particle 2 both have kinetic energies of 1/2 joule, or you can say the combination, the pair as a whole, has 0 translational energy, but they have a relative kinetic energy of 1 joule.